Good morning. So next week I will finish lectures. So we have lecture today. I continue on the string vibrations for the finite string. So it will be connections with oscillations that we saw before, and then next week there will be 3 lectures. One on nonlinear waves. Another on dispersion, and the third on a combination of the two. So we finish the next week. I'll give one more list of exercises today. It's for for Monday, not that Monday, but the next Monday. And then you have Carnival. Who wants to give a pass exam? It will be written. We already set the date, no? It's probably. Let's repeat it. Let's see what was the date that was set. It was a long time ago, but yes, we set the date for the exam to. So day 27, you still can meet probably the monitor, so I don't know what you fix with him, but probably 27 would be good. But anyway, exam will be on day 28 at the same time. I think the same room, unless if something happens, I'll leave the note. But I think this will be the same room. Okay, and then okay, that's an idea. So day 28 will be for exam, and 1st of May, and you can combine with the monitor either. For example, next day you can make an analysis of all the problems if you like. Yes, but this is with him by him. So that's an idea. So that just between next week and 28th of March, you will have like 10 days to just try to revise all what we had. I will have problems which are more or less in line with the lectures. So, well, usually I allow during exam to use whatever notes that you have, so it's okay. I think so. Well, usually I do this. So if it will be different, I will let you know in advance. But I think it's okay. Good. So where we stopped with the wave equation. Usually we will mostly consider one-dimensional problems because we have just very few lectures on waves. So I want to give you some principal ideas and give some taste. So certainly I cannot give you much on the waves. So, but in 5 lectures, in a simple way, we will cover some interesting topics. So this is a wave on wave equation on infinite line. So when you consider string vibrations, for example, string of the guitar, then we know that string is fixed at 2 different sides. So the u in that case is the deviation from the central line, and x is coordinate. And in that case, so there is one side, another side, and what we know for the string vibrations is that a is square root of t over rho. This is what it should be. Let me check. Yeah. So it's a tension, the force that you put to stretch the string divided by the linear density of the string. So essentially, in other words, it's force divided multiplied by length divided by mass. So what is density is mass divided by length, right? So like this. Okay, and in that case, equation or wave equation is valid for each point of the string, but then, but additionally we know that ends are fixed, so we have boundary conditions. Boundary conditions, which is u at u equals 0, at x equals 0, and x equal L. So at both ends, the u is just 0, right? So, okay. So we fix the two ends. So we need to solve this equation. So we know how to solve that the wave equation on the full line. So now the question, how you solve the equation if you have ends fixed. And the way how we will solve it has to do with technique from analysis, which is called spectral method, and it is based on Fourier series. So the first topic I'm going to give is a Fourier series. Okay, so Fourier series, by definition, it's we define Fourier series as the function given by the sum. This series, so it's sum over all integer numbers of some coefficients, exponent I is plus nx. So here coefficients are complex numbers. And what we assume is that this sequence converge absolutely. So it converges absolutely. So it converges for any x. In order to ensure it, you can just assume absolute convergence. It converges by taking absolute value of each term. But when you take absolute value of each term, exponent gives absolute value 1. So it's just sum of absolute values of Cn converges. So this is what we assume. So this is a Fourier series. Okay. So as I said, that Cn is complex, exponent is complex. So what you can do is that you can check what is the condition for the. So if function is real values, right? So so here x is real, no? So if function is real, what you should have is that f of x should be equal to complex conjugated. And complex conjugated is what? So you take this sum and complex conjugated. And in exponent, you just give a minus. So next step, what you can do is you change n to minus n. So you change sign of n, right, in the sum, because you sum over all integer variables. And you get sum over all n of c minus n complex conjugated, exponent minus nx. So you see that this should be the same as that, right? So this function should be the same as the original function for all x. So this gives you a condition for the coefficient. So that for real function, every Fourier coefficient is complex conjugated to the coefficient with minus n. So that's conditions for the function to be real. Okay, and in principle, what you can do, you can define So from this, what you have, so that what you have is that you can define C0. Well, let's define. Well, it will be clear what's for. So C0 we associate with coefficient A0, which is real. So C0 is real, right? Because C0 is complex conjugated to itself. So C0 is real, and every Cn gives you has a real imaginary part. So let's denote real and imaginary part by A and B, n divided by 2. So if you take, this is general form of the coefficients, and C minus n would be an plus ibn over 2, yeah, complex conjugated. So this is general form of the coefficients that you have in the Fourier series, because they should be complex conjugated. And then if you substitute this into the function, the imaginary part will be 0, yeah, because that's exactly the condition that we checked. And for real part, what you obtain is, so what you obtain is f of x. So for n equals 0, we will just have a0 over 2. And then there will be sum from n from 1 to infinity over natural numbers now. And then you can sum Cn exponent plus C minus n exponent minus n. And you take a real part of it. So what actually will be, so what you can check is that this will just be, okay, let's write. So this will be Cn I n x plus C minus n minus I n x. And you put this. So we now only take real part, right? Because imaginary part we already know is 0. The real part of this will be an over 2 by an over 2 cosine nx minus, and then it will be minus b by I give minus, so it will be plus. And you can check that this term will give just the same, because it will be a by cosine minus nx, which is cosine nx. And then it will be minus bn sine minus nx. So it gives you minus to minus will cancel. So actually 2 will come out. So check this condition. So that gives you another form of the Fourier series, which is intrinsically real. So it's how you write it in. So this is a real form of the Fourier series. For real functions, they're equivalent. Okay, good. So now we will prove some sequence of theorems, which exactly explains why this how one can work with this series. So first of all, if the function is given this, so for function given by the Fourier series, if you're given a function and you know that it was given by Fourier series, you can find coefficient. So Cn equal 1 over 2 pi integral from minus pi to pi f of x exponent minus I nx. dx. So you can find, if you given function generated by Fourier series, you can make a backwards transformation, you can find coefficient. So here, the good observation to do is that in the Fourier series, you see that every exponent is a periodic function. And all of them share the same period. So all of them have a period of 2 pi. So that means that function of f of x is periodic. A periodic with a period exactly 2 pi. This is from, because every term is periodic with this period. So that's why it's actually, you can choose, and this function is periodic, so you can actually choose any interval of size 2 pi. So you can integrate from minus pi to pi, from 0 to 2 pi, whatever, which is the same value. So let's prove this theorem. The proof is very simple. Essentially, proof is just you substitute this sequence to the integral. So let's just compute this integral. You substitute the sum. So now we already have n here occupied, so we will consider sum with respect to m. Right? So there will be no confusion about indices. Cm I mx by exponent minus I nx dx. Well, the next step is that this sum is absolutely convergent, which means that you can commute integration with the summation. So you put sum of the integral minus pi pi, and Cm is a constant, so let's put it out as well. M minus n x dx. So the next, what you should check is that the integral over the period of this function so what it is. So when m equal n, this is just 1. So it gives you 2 pi. And if m is not equal to n, you give the same exponent with some prefactor. But exponent is periodic, then it gives 0. It was 0. So it means that this sum will be only non-zero when m equal to n. So this is just, and it will give you 2 pi. So it will be 2 pi Cn. And that's it, because it gives you Cn as this integral divided by 2 pi, which is our formula. So that's first condition. And what you can do also, so it can be a simple exercise for you. So if you have a formula for Cn in a complex form, then you can also derive formula for A and B, so for real coefficients directly. So what you can check is that, well, A0 is just twice, A0 is 2C0, right? 2C0, so we take 0 here, 2 cancels 2, so it will be 1 over pi. Exponent will give 1 over pi of the integral. Then you can find An. So what is An? It's again, it will be 2 times real part of Cn. And real part of Cn is cosine, right? So again 1 over pi and Bn, you see Bn, it will be minus 2 imaginary parts, but imaginary part is sign of the minus, so minus will cancel. So it will, at the end it will come out with plus. And sine of nx. So that's formula for the real coefficient, Fourier coefficients. So you see now this formula is general because n equal, when n equals 0, you recover the first formula. So essentially this is general relation. Okay. The next theorem will tell you so let f of x be smooth, so infinitely differentiable function on a circle. So it's a periodic function, so we're in a circle. And this is a space of periodic functions, infinitely differentiable functions. So smooth, in other words. So consider this a smooth function. Then for any a, so any power a bigger equal to 0, and there exists a constant c. So what means c is it will depend on f and a, so it depends on function and this constant, but independent of n, such that modulus of the Fourier coefficient, so this is what we call Fourier coefficient. Fourier coefficient, in principle, you define for any function f. So this is Fourier coefficient. You given function f, you can define Fourier coefficient. So that's by definition 1 over 2 pi is bounded by that coefficient c and by modulus n minus a for all n which are non-zero, no? Because for 0 it doesn't make sense. So what this means, it means that if you give me the function which is smooth, then the Fourier coefficients will decrease for large n bigger than any power, faster than any power. So you see, so any power of n you take, so the Fourier coefficients, they go to 0 faster than 1 over n squared, 1 over n cubed, 1 over n 4. So any power is faster than any power of n. So it's faster. It goes to 0 faster than any power law. In fact, from complex, if you have a complex analysis, you you'll see that it goes exponentially fast for analytic functions, but for infinitely differentiable, it's just faster than any power. So it goes down, it goes to zero very fast at large n. So how you prove it? Okay, let's start with a equals 0. So essentially, we need only to, it's enough to check this for any a integer, yeah, because essentially it's enough to check this for any integer, arbitrary large integer a, and then it's automatically true for any a, right? So it's kind of clear. So let's check it first for a equals 0. So what we do, so since modulus of n is this expression, we can take this expression is smaller than absolute value, that integral of the absolute value of the function. So smaller or equal than 1 over 2 pi of the absolute value of what is inside. Right? And if you take absolute value, exponent will disappear. Let's put less or equals, it's more convenient. Dx. And this is just exactly our function, our C. Let's call CA. No, CA. This is our CA. C0. No. This is our C for A equals 0. So you see, this is exactly, we proved that Cn is smaller than Cn power 0. So smaller equal than C. And this is what we proved. So we proved it for A equals 0. This theorem. So next, let's prove it for A equal 1. So how you do? You take Cn by this function, by the definition. So what you can do is, instead of exponent, we can write derivative of the exponent. When you differentiate the exponent, you get the same exponent by multiplied by I minus in. So you should also put this minus in in front. So this in will compensate what will come out from derivative. And then we integrate by parts. Right? So we integrate by parts. So it gives you minus 1 over 2 pi in f of x exponent minus in x between minus pi and pi. And then minus, but we already have minus here, so it will be plus. And then you pull the one derivative from here to there, to f. F prime of x exponent minus I and x dx. Where the first term, this function is periodic, this function is 2 pi periodic, so they're both periodic, so this is 0. Okay, so now we can compute absolute value of Cn. This is smaller or equal then absolute value of the whole version. So then absolute value of the prefactor will be 2 pi modulus n. And then there will be integral. And then it's smaller or equal by of the absolute value of what is inside. Again, absolute value of exponent is 1. So we take it 1 over 2 pi. Let's put 1 over n at the end. So it will take integral of minus p modulus f. Here's a prime, no? Prime dx 1 over, and then modulus n minus 1. So this is a coefficient which does not depend on n. And then this formula just proves our theorem for a equal 1. Yeah. And so on. So what you can do, you can take this formula and again make an integration by parts. 1n will come out, will go to the denominator, and you get second derivative. And you get you will prove it for a equal 2, and so on. So you can write the general formula for what you obtain after n times integrating by parts, and it will just give you this formula for different a's, for different integer a's. This is ideal. This is how you prove the theorem. Okay. So the corollary from this theorem is that for any, so given for any function f which is periodic and smooth, the corresponding Fourier series where Cn is given by this integral converges. For all x. So if you take function which is smooth, compute Fourier coefficients by this formula, and then form a Fourier series, it will converge. So it will give us some function. We'll not erase it so far. So how you prove it? So proof is rather simple because for convergence it's enough to show the absolute convergence. So we can prove absolute convergence. So the sum. So it is sufficient to prove the absolute convergence. So if this series converges absolutely at every x, it also converges. It's obvious. No? And the good part of the absolute convergence is that the absolute value of exponent is 1, so it doesn't depend on x anymore. But now we know that it's smaller or equal to this expression for any a. So you can take it for any a with different coefficients. But for example, you can take n minus 2. And this is finite. So we have absolute convergence. That means that the series converges absolutely. So now it's good to understand where we are at the end. So there are different expressions here that we found. The first expression that we found that let's make a diagram. So what we found that if for f of first theorem was given that if of f of x is given by the Fourier series, then Cn is this expression. The second theorem was telling us that if f of x is smooth, then this theorem, the corollary. It was telling us that then the series converges. Okay, sum over n, Cn converges for Cn equal and you see that this is somewhat different expressions, right? So the first tells you that if function is given by the sum, you get coefficient. And the second tells that if function is arbitrary, you can compute coefficients and the corresponding series converges. So the only missing part is to prove, to see whether this is the same as f. So the question if this is equal to f of x or not, right? So this we didn't prove, right? We proved that if f of x is this series, okay, Cn is this formula. Now if f is arbitrary but smooth, take Cn by that same formula, form a series, it converges. But we still don't know if it is if it will be the same function. So there is a final theorem that we don't prove because it's already more complicated, and you can look at it at the analysis. Slightly, I don't think it's given by on the analysis on the line course here, but in general in analysis you prove it. So I'll give you the simple version of this theorem. So if function is, so you don't need to S infinity. So for example, the simple version of the theorem is that if a function is twice differentiable, twice smooth differential, so it can have first derivative, second derivative, and derivative are still smooth continuous functions. So then f of x is the same as the corresponding Fourier series. So whenever a function is twice differentiable, is indeed you can compute for your coefficients, form the Fourier series, it will be the same thing. All right. So so this C2 theorem, I think you can see the proof in the Arnold's book that I have in list of literature. But in principle, C2 is not necessary because this function is correct under way more weaker conditions. So it's not doesn't even have to be continuous. But there are some details, right? So, for example, if f of x is measurable function, it's still so you have many other versions which are much weaker than this, but okay. Measurable. It's okay to be measurable function. It doesn't even have to be continuous, so it still works. Okay, so that. But don't worry. So the idea is that if function is sufficiently regular, it works. It also works if it's piecewise regular and continuous. Piecewise twice differentiable and continuous, then it also will work. I think piecewise smooth functions is almost all what we cover most of the cases that we see in practice. Okay, so that's our technique that we will use, and just it's good to give some simple interpretation of geometric interpretation of what the Fourier series is. So let's remember what means basis. Basis in a linear, so if you consider in a linear space, you consider any linear space, for example, you consider n-dimensional space, then basis is some set of n linearly independent vectors. In which case you can take in that case you can one can express any vector as a linear combination, right? So it's like I from 1 to n. Correct? So that's the idea of the basis. Yeah. So then we can also always, given some basis, you can, well, not all, let's say, you can also define what is orthonormal basis. So orthonormal basis is a basis such that any two vectors, if you take scalar product between the two, so it will be 1 when I equal j, and it will be 0 when I not equal j. Essentially, what that means that your vectors u1, u2, u3, well, all of them has unit 1, so the size is 1, right? So the length is 1 because scalar product with the same gives a square length, so it's 1, and all of them are orthogonal to each other. So that's orthonormal basis. So they're all orthogonal, and the size of each vector is 1. good. Oh, see, starting to follow my mistakes. This is good. So then let's consider the space of these functions. Or let's consider this linear space of functions, of periodic functions. So it's smooth periodic of smooth periodic functions. It's still linear space because we can add, multiply by constant, so it's still linear space. And we can now define what is scalar product. So we define a scalar product, f and j. So if you have two functions, f and j, we define a scalar product, so we put a definition as 1 over 2 pi integral. So periodic function of let's say smooth complex valued periodic functions. So given any two functions, f of x, g of x, which are both smooth and periodic, we define the scalar product of f with j as 1 divided by 2 pi integral over the period f of x, j of x dx. Okay, that's extension of the linear space, so that's probably better for you to consider complex linear space. Right? In that case, remember, okay, let's not complicate too much. Okay, that's scalar product is for the complex function. So the only thing is you put complex conjugation to G. So that's the same as scalar product for complex vectors. So we take complex vectors. You have in a scalar product you will have to put complex conjugated to the conjugation of the second. And that's why because when you take scalar product of f with f, this gives you f complex conjugated f, so it gives you modulus squared, right? So it gives you positive numbers. So this is why it's needed. So now, first of all, so now we can define functions which I called E n of x, and we take these functions to be those exponents. Exponent I and x. Okay. So that's every function of the for every integer number. So that's a function which is periodic and smooth. So now first what you can check is En Em scalar product is what? Is 1 over 2 pi integral minus pi exponent of I and x, and then the second should be complex conjugated. The x, this is 1 over 2 pi, the integration of E I n minus mx dx, and this we know. So this is when n equal to m integral, this is 1, integrals 2 pi cancels 2 pi. So this is 1. And when n is different for m, this is periodic function, integrals periodic functions that it will give 0. So we already know that this is orthonormal subset set of functions. So we have orthonormal set of functions. Now, what means projection of any function to this vector, to this E? So f to En, by definition, so this is exactly the same that you would project any vector U. This is what I didn't write. So in that case, I forgot. So in that case, when it's orthonormal basis, you can write every coefficient Ci as, and better we put a basis. Let's make it exactly the same. So E, so we take E, 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 E. So in that case, in case of vectors, if the base is orthonormal, so in order for finding the coefficient, you just multiply by EI. Yeah, because you multiply by EI, all products will be 0 except for the right one. So here we will see that it's exactly the same. So f by En is 1 over 2 pi integral f of x, and then you take conjugated E's, and this is exactly Cn, right? So by definition, Fourier coefficients. Good, no? So same thing, and the last is given by the theorem. The theorem tells us that f of x is equal to its Fourier series, which we just write sum of on L integer Cn. So you see, it's essentially very similar to what you have in usual vector space. So somehow you can think of these functions as vectors in infinite dimensional space of functions, right? E4 and so on. So all of them are orthogonal to each other. All of them has size 1 according to the norm which is induced in this space. And the Fourier series is just expansion of the function in the basis with this function. So that's an idea of the Fourier series. So it gives you orthonormal basis in the functional space, and Fourier series is just expansion. Okay, so let's make a short break. Okay, and we'll continue. So a bit slow. Too slow. Okay, so now let's go back to our string. So what we want to solve, so we consider string, which is fixed at two sides. U is deviation from center line, x is a length. Okay, so what we will do, length is L, but you always can change x redefined by constant, so the size will be 2 pi. So let's just already from the beginning simplify our life, so we consider string of size 2 pi. So otherwise divide x, multiply x by 2 pi, divide by L. So what we have in that situation, we have the wave equation with the boundary conditions. So the u is equal 0 and u at x equal 2 pi, both 0. So, so what we will work is with the spectral method. Today. So what you do? Essentially, you do something similar to what we were doing with linear systems in part of oscillations. So, for example, you can see that the coefficients do not depend on time. For example, if the coefficients do not depend on time, you can use the function of u as exponent. Then every derivative will still be exponent, so you know the exponent will cancel from all the terms. So let's do this straight away. So we take u and we guess it in the form of some function of x that we don't know. An exponent, in principle, remember, always exponent was of a complex number by time, but I already know the answer will be purely imaginary, so I'll put I. Okay, but in principle, you may just put exponent lambda t as we always did before for finding eigenvalues, eigenvalues. So this is lambda is an eigenvalue. So you substitute this into the equation. So the twice the double derivative gives you minus omega squared. Minus a squared. And the second derivative of x equals 0. Exponent cancels. And then multiplied by remove minus and divided by a squared. So you get phi double prime plus omega squared by a squared, which you can write like this, equals 0. And this is harmonic oscillator, right? So we know what it is. So then any solution of this equation should be cosine and sine. Okay, A and B are arbitrary so far. So now, using the fact that u of at x equals 0 is 0, which means that phi at 0 should be 0, right? It's fixed on the left end, so phi should be 0 at the left. And at 0, this sine is 0, so cosine is 1, so it means A is 0. Okay. Now, as long as A is 0, so we have phi of x equal b sine omega ax. And we consider we want B non-zero, right? So this is a linear system. So now B is arbitrary, right? So if it's solution for one B, it's solution for any B. So we want to be non-zero, be non-zero because zero solution is not interesting. So B non-zero means that this should satisfy. So now we can check the second condition. So this implies that sine omega A by 2 pi is 0, right? Sorry, pi, okay? Not 2 pi. I take length. I want pi. Not a big difference. So I don't want 2. Length will be pi. That is 0 if prefactor is integer, right? So it means that omega is plus minus a n, where n is integer. So what we have a collection of, we have particular solutions which are this exponent by, let's take this exponent by phi, so it will be, we take a solutions which is, let's take b equal 1, so the solution will be sine omega divided by a is n, or no, plus or minus doesn't matter because it's just absorbed in B. So n so omega of by n and x by exponent I, and omega is now an, so a n t. So this is a solution that we found, particular solution. So this is what we found, that this is solution for any n. So we don't need to write it positive or negative because it's for any n. Oh, okay, let's keep it. So then this is complex expression, but we know that if this equation is real, with linear with real coefficients, then real part of in imaginary parts are solutions. So we get solutions sine nx by cosine a and t, and also another solution sine nx by sine a and t. And then we get a solution, the solution, the genuine solution. We will see that it's genuine. So for now, we don't know the solution. It's a linear combination of all of them. So there is no n cannot be 0 because it gives you just 0. So we take n from 1 to infinity. Because for n positive and negative, it's just this, it gives just the same expression up to sine. So we don't need to consider negative n, and this will be arbitrary coefficient prefactor by the first cosine. We'd start with the temporal part, sine And then I put the spatial part. Okay, so that's a solution for the vibrations of the string. Oh. So what you see is that vibration of the strings is a linear combination of modes. So n equal 1 is just sine x. So it's in this mode, which is just multiplied by periodic function. So it's vibration of the main mode, which is usually called fundamental tone. That's main motion that you see in the guitar. But then there are others. For example, when n equal 1, so n equal 2, the shape will be sine 2x. So it gives you that motion and so on. N equal 3 will be like this. So that's a general solution. So that's a solution that so far we don't know is it general or not, but it's a solution. So now let's show that this solution is general. So it can solve a Cauchy problem. So it means that we can give arbitrary initial condition and write solution in this form. So we take initial time and we say that at initial time u is phi of x and du dt is psi of x. Just the same way as we did to find the D'Alembert solution, but so we take initial position and initial velocity. And let's see if given initial position and velocity you can find the coefficient. You can find coefficients such that this expression satisfies the initial conditions. Then for any time, this is the solution. So we need to prove that we can choose coefficients such that we satisfy arbitrary initial state. But of course, you see this initial condition should satisfy also boundary conditions, right? So we certainly need that phi 0, phi pi, c 0, c pi 0. Okay, so what do you do? So let's take this function phi. And is defined on the interval between 0 and pi, right? So this is where initial condition is defined, because our string is between 0 and pi. So this is our function. So let's say this is our phi. So what we want to do, I will extend this function until 2 pi just by taking the mirror. I'll take the reflection with respect to that point. Okay? And then I can just continue it periodically. So I can from one piece of the function between 0 and pi, I can just by the reflection I can compute, I can extend this function to period. So we extend phi of x to a periodic to a 2 pi periodic function. So that's why I consider I wanted to have a string to have size pi, because then we get periodic functions of 2 pi from reconstruct from any functions which is 0 at both ends. So we can do this. And next, so that function actually will not be twice differentiable, but it will be piecewise twice differentiable and continuous. So that function is still works. This theorem still works. So what you can do is you know that now phi of x can be written as a Fourier expansion. So the general form of the Fourier expansion, let's use now the real form of this Fourier expansion. So this is real form of the Fourier expansion, and also remember what are the coefficients. The coefficient an is 1 over pi the x, and bn it's just our theorem, but I just like now to use real form. Why I like to use real form? Because the function phi it's odd function, so it's, you see, it's from plus to minus, it changes the sign. And then the cosine is just the other form of the function. The cosine will be cosine like this. Right? So what you see that when you multiply by cosine and integrate, what you get here is minus of what you get there. So you get, this is 0. And Bn is not 0 in general. So what you conclude is that phi of x can be written as a Fourier expansion just of the signs. Right? And there is not exactly the same thing you can do with psi. Okay. From 1 to infinity. And then I will write another function. I will write tilde just to show that it's the same. It's a different coefficient. You know, the coefficients are written by the same formula, but you have to put psi here. So we can write a Fourier series for the initial condition. And we are almost done. Because now let's take our general solution at t equals 0. So let's just substitute t equals 0. Sign will will disappear, cosine will give 1. So general solution of t equals 0 will give you ux0 is what? Is sum of on a n from 1 to infinity of a n sine nx. And this should be our initial condition. So you compare this expression with that expression, and then you find that this is satisfied if an is taken to be Fourier coefficient of the initial condition. So this an taking Fourier coefficient of the initial condition, you satisfy automatically the first initial condition. And taking derivative at t equals 0 gives what? Gives, what is the time derivative of this expression? So du dt equal will be sum an derivative of cosine will give you minus an sine ant plus bn an cosine ant. This should all be taken at t equals 0, and then sine nx. So this is derivative computed at time 0. So what it is, the first vanishes, the second gives 1. So it will be sum of n equal 1 to infinity, bn an sine nx. And this should be equal to psi of x. Okay? So which is the same sum, the same Fourier sum, but with given Fourier coefficients. So you can satisfy the second initial condition if you take bn just to be the Fourier coefficients of the initial condition divided by an. That's it. So this shows how to solve. It gives you unique. So we say that we find a solution of the Cauchy problem. Yeah, so you give me, so how you proceed, you give me initial condition. Where is it? Here, you give me initial condition for position velocity. What you have to do, you expand them into the Fourier series. You know how to do it because you have a formula for coefficients. And then you just take A capital, B capital in this form and cook up the solution. Then you find solution at any time. Yeah, so you find solution at any time, and this solution will be sum of this of the functions of different modes. So this is fundamental tone. This, well, I think it's more from music. So this is called overtone. So n bigger than 1 is overtones. So sum of the tones. So that's exactly what you hear when you play the musical instrument. So you put a string and you hear the combination of these functions. That's in particular why notes from different octaves you hear similarly, because they're composed of exactly the same functions but with different amplitudes. You see, if you take length, you can see that if you take length of the string twice smaller, then you will just hear all overtones with corresponding to even ends, because they pass through 0 here in the middle. So if you pinch it in the middle, you will hear the overtones, and the song will be similar. So if you just play the full string it will be one song, but if you pinch it in the middle, you will just only remove the odd tones and keep the even tones. So that's why you hear something very similar. Good. Okay, so I think we succeed to do. Okay, so the next topic which I must give today is what happens. So that's ideal situation when there is, for example, no dissipation. So, but we know that whenever you play the guitar, if you play the string, it vibrates. Initially, it's well approximated by this solution, but if you wait a long time, its amplitude decreases and it stops. So there is dissipation. So there is something which decreases the amplitude with time. So the question how you can incorporate this dissipation into your wave equation. So wave equation with dissipation. So the good part is that you can derive the dissipative terms in the equation without even thinking about physical origin of your system. And what means dissipation? The dissipation usually means that energy goes from macroscopic to microscopic form, and this is irreversible process. Time irreversible process. So now, if you have dissipation, looking at the system at increasing time or just changing time and decrease time, it will be two different. It will not be the same system. So we violate this hypothesis, which was in the, in our enumeration, it was hypothesis 5, which is time reversal symmetry. So remember that in derivation of wave equation, we had this symmetry. We used this symmetry, and now it's violated, so we don't have it. So essentially, we have to put back the terms which we removed because of this symmetry. So, so this H5 was used to remove odd order derivatives with respect to time. So now we put them back. But there is one moment that remember that using long wave approximation, we only need lowest order derivative. So we put them back, but only to the lowest order derivative. Remember that long wave approximation tells you that more derivative I take, smaller the term under this condition. So we have to put back the odd order derivative term, but only keep the lowest order one. So which is the lowest order derivative with odd derivative with respect to time? Huh? Du dt, no? So du dt is the first. Is the first option. So it's odd order, first order, and it's the lowest order. So any other derivative will be higher order than that. Okay. So this gives you an equation with a dissipation. So the wave equation. So, okay, so the wave equation will take the form the same terms that we had, and we add one more term, which is this one, plus epsilon du dt, and then we keep what was before. So this is dissipative term. That's it. So just from general consideration, we found what term it should be. So we have to say that the observation is that the physical meaning of this term is external. It's linked to external dissipation. For example, interaction of string with air. So why? Because you see that this is just derivative of u. So if you don't change the shape, but just go up and down, it should give the dissipation. It should give effect. So this is this dissipation only. It essentially works where you have it's non-zero when you have motion of the system as a whole. So in some cases, for example, sound in air. When the sound propagates in air, and this is the equation for sound propagating in air, if your sound just move if you move all volume of the gas of the air without any deformation, there will be no dissipation. For dissipation, it needs to deform. So dissipation requires deformation. So in other words, in that case, epsilon is 0. So just this term is forbidden. So in that case, we need to higher order terms. So in order to, if you want to describe dissipation in higher order terms, still they have to be odd order and lowest order. So then there are two terms of this type. So one of the terms will be cubic, right? But then there is another term. Which is third order derivative. This is once with respect to time, odd number 3 times. And here we also add x cubed. So any other term will be higher order. So this is the two most important terms, and a priori we don't know which one is important. But the next thing is what you can do is you can show that these terms are actually have the same meaning. So we don't need to take into account both of them. So if dissipation is small, if dissipation is small, so if the term that we add will just have a small effect that we can still use. We can approximately use the wave equation. So this term is approximately that, right? Wave equation. And then what you do? You take this term and remove one of the derivatives outside. Use the wave equation. And you see that this term and that term is just they equal up to constant. So what it means that in the first order approximation, these and these terms are just the same thing. So and are equivalent in first order approximation. Up to constant. So they are approximately equal to each other up to constant. So we just can take the one that we like. So we take the second one. So from the first equation, we choose wave equation with external dissipation. Under condition that now external dissipation is 0, we get another equation. I will put it with minus 2 gamma for a purpose. We will see why. So this is so far, it's just arbitrary coefficient epsilon, negative, positive, and gamma can be negative, positive. So it's positive, so I can put constant whatever I like. And this is another equation of wave equation. So this is wave equation with now internal dissipation. So this is a dissipation which only acts when you have deformation, because you need second derivative of u. So for the string, it will depend. It will only be true if the second derivative changes. So essentially, the string should deform. So if the second derivative changes, second derivative is the curvature. So the curvature should change. So when the string vibrates, it always changes curvature from 0 to something, and then this term is active. So this will be a term which describes the dissipation because of deformation of the string itself, and this term would define the dissipation due to the interaction with the air. So whenever this term is not important, you should use that. And let's just solve rapidly that equation. So now we go in the same way. So we'll look for the solutions. So we look for a solution in the form uxt. And now what I will write exponent lambda t. Now I know it will not be I omega. Before it was purely imaginary. Now it will not be purely imaginary by some function. If I put function, just the same analysis will give me that this function is actually sine nx. So I just simplify the life. Keep sine nx. So this will be eigenvector. A priori unknown, but for analysis you will see that it will be sine nx. So let's just concentrate on finding lambda. Okay, so let's be it's n. Okay. Well, let's put k because n I will use n for the Fourier series. So k. So k is 1, 2, positive integer. Okay. Anyway, I have a right to look for a solution in any form. So I look for a solution in this form, substitute it into the equation. So what you get from the second derivative, you get lambda squared. From minus gamma minus 2 gamma. First derivative in time will give me lambda, and second derivative in x will give me k squared with minus. So we put plus. Kx. And then minus a squared, second derivative. Second derivative of sine gives you minus. So it will be plus a squared, k squared. E lambda t sin kx to 0. So we're only checking equation of motion because boundary conditions are already automatically satisfied. So it's 0 on both sides. So now we can cancel sine, which already justifies why we use it. We cancel exponent. And what you get is the lambda squared, just 2 lambda k squared gamma, or lambda, plus a squared k squared equals 0. Quadratic equation, so we find lambda. Where d is gamma 2 k4. Well, remember, quote so quadratic equation. So first of all, for stability, we need that real part of lambda is negative, at least, or non-positive. So this already tells you that since there is plus and minus, that gamma should be positive. So it means that whenever you use the model for the internal dissipation, it has this term with positive prefactor. Because if the prefactor is negative, it will be unstable and, okay, so dissipation, it will be growing solution. So the solution will grow, which is already against the concept of dissipation. Dissipation cannot give increase of the solution. So dissipation should give, is gamma is negative, positive, and then we can just analyze what we have. And we have two situations. One situation is when discriminant is negative. If the discriminant is negative, so what it is? It is k square gamma square k square minus a square, right? No, actually, yeah. So it is negative when k is small. So when k is smaller than a divided by gamma. And discriminant is positive if k is larger than A divided by gamma. Good? And then we just interpret this solution. So if D smaller than 0, which means K is smaller than, I will just repeat what it is, A over gamma, which means that lambda is equal to minus gamma K squared plus minus I omega. So omega squared will be minus D, so modulus of D. No. Square root of D. So what you have is that for modes which are not so high modes, like K equal 1, K equal 2, until this value, they will oscillate and decay. So these modes will give you solution. They will behave as exponent as the sine kx multiplied by exponent minus gamma k squared time, and by the cosine or sine omega t. Right? So they will oscillate with this frequency, decay in amplitude, but oscillatory. So now for the high modes, when D is positive, so K is large, the lambda, both lambdas will be minus gamma K squared plus minus square root of D, and they both real. There will be two lambdas. And then the solution will take the form sine kx by one exponent t plus another exponent t. So both lambdas are negative. So what will happen is that for these modes, which are modes sufficiently high k, so this is k smaller than k star, which is this, and this is k bigger than k star. These modes will not oscillate. They will just go to rest without oscillations. Just die. So that's what internal dissipation does. So first, and linear combination of all the solutions will give general solution. But anyway, so what you see is that whenever you have internal dissipation, only large order modes oscillate, and after a long time they just oscillate, go to the rest. But very high order modes, you will not even hear them, because they will not oscillate, will just go to rest directly. And this is very similar to the action of the dissipation on the pendulum, if you see. So if the dissipation is large, pendulum was oscillating, going to rest oscillatory. If dissipation is small, if its dissipation is large, it goes to the rest without oscillations. And this here, the difference is between modes. The principal modes with small k, they will oscillate before going to the rest, and high overtones, they will just go down without oscillations. So probably I will, for a few minutes, I will give you the exercises. I can give it on Monday, but probably good to give it before. Yeah, so you can already start thinking. This is the last set of exercises. This is x. List should be 6. For February 20. So it's either you give it, either you find monitor or just send it by email. Better. So the first exercise, take the wave equation on a full line and using the D'Alembert solution. Never remember how to write this. Construct graphically the D'Alembert formula. Construct graphically, just like we did on a class, a solution for positive time from initial condition when the initial u is 0. So and the initial velocity is psi of t, and then you take psi of t pi of x. Psi is, so you have a medium which has 0 shape in the beginning, but velocity has some velocity. For example, if you can think of the way of the surface of the water, and then you pushed it in the middle, right? So it's still in the initial moment it's straight, but it has initial velocity. So how this initial perturbation will evolve at large times? So you just make a graph. And then the other two are from here. So there is take a string of size pi and consider initial condition so phi of x will be x when x is between 0 and pi over 2, and it will be pi minus x between pi over 2 and pi. So essentially what you do, you take your string and you pinched it, just like you do with musical instrument. You pinched it right in the middle. So the initial velocity is 0. Just shape. You pinch and leave it. So you take a string of the guitar and release. Find a Fourier series solution. I found the Fourier series solution for any phi and psi. Just make this computation of the coefficients for this particular form. So compute what will be coefficients, so you will find the solution. You will find, in that form, you will find what will be the shape of the string at any time bigger than 0. So how it will behave. If you like, you can even practice drawing this on a computer, so see how it will oscillate in time. It's an interesting experience to see it there. And then finally, perform analysis of eigenvalues, actually eigenmodes. The same analysis, I did this for the eigenmodes for the external dissipation. Do the same for the internal dissipation. In case for wave equation with external dissipation. In particular, you will see that for stability, you will need epsilon to be positive, and you will see that actually with the external dissipation, the behavior of modes is different. So it will not have such a drastic difference between higher and lower order modes, but there will be some difference. Just do the same analysis, but with external dissipation instead of internal. So you'll see that what is the difference between the action of, for example, the internal, the dissipation in the string with the dissipation due to the air. So they act very differently on high and low order modes. And so some of them are more important for high modes, some of them are more important for low modes. That's it, no? Yeah, that's it. So these are exercises, and that's it. Thank you.